This video is going to figure out how old and how big the universe is based on data by galaxies that have been published in the astronomical literature and compiled into NASA's NED database with distances and velocity measurements. All these plots here, all these points in the plot, are plotting a galaxy, a different galaxy, and this is the distance it is away from us, and this is the velocity. It's moving away from us. So all of these galaxies are moving away from us with a given velocity, and they're a certain distance away from us. And those two things have been measured independently. So now that I've described that, let's read the problem statement. Each point on the plot above represents a galaxy where the distance and velocity away from our galaxy have been published in the astronomical literature. Distances were found mostly using standard candles such as variable stars. The units are kilometers per second, which is about Mach 3, and millions of parsecs. 1 megaparsec is slightly farther than the Andromeda galaxy. So the Andromeda galaxy is actually right here. You can't quite see it because it's coming toward us on this graph. This trend appears to be proportionality with a slight offset in velocity to the motion of the Milky Way toward the Andromeda galaxy. This trend is called Hubble's law and can be written V, which means the velocity, is proportional to r, meaning the distance away from Earth. Now, before we move on, I want to say a couple things about the history of Hubble's law. The first thing is, Hubble probably should not be the person to receive credit for Hubble's law. He was a very good astronomer at a very good institution with access to the best telescopes in the world, yet he tended to get credit for a little more than he actually did. For example, the velocity measurements of galaxies in the early 20th century was primarily done by an astronomer named Vesto Slipher, who made a whole bunch of measurements of the speeds of galaxies and then made correlations between the speeds of galaxies and maybe their shapes and where they were. At the time, nobody knew whether or not galaxies were inside our galaxy, the Milky Way, or whether they were outside our Milky Way, which was referred to the island universe theory, which was originally thought up by Immanuel Kant. What Hubble did do that was extremely important was he compared Cepheid variable stars as seen in the Andromeda galaxy to Cepheid variable stars that had been published by an astronomer named Henrietta Leavitt of the Harvard College Observatory in a satellite galaxy to the Milky Way called the Small Magellanic Cloud. She also worked them out for another small galaxy around the Milky Way called the Large Magellanic Cloud. They're referred to as the Magellanic Clouds because they're named after Magellan, because you can only see them from the southern hemisphere. That said, Hubble's law was really first discovered in kind of practice and understanding by a Belgian priest who was a theoretical physicist whose name was George Lemaitre. And Lemaitre had come up with a solution to Einstein's equations of general relativity, which were his theory of gravity. Lemaitre showed that Einstein's theory of gravity was stable for an expanding universe. He called this the primordial atom, the small nugget that began the universe. Later it was criticized as referred to as a Big Bang, and now it's the Big Bang theory that's the name that it is associated with it. So Lemaitre pretty much figured out what we now call the Big Bang Theory. So now we put it into context. Let's see what this asks us to do. The first thing it says is, take out a ruler and draw your best fit line through the points. Measure the recessional velocity, remember recessional means moving away from us, on your trend line at distances of 20, 40, 60, and 80 megaparsecs, and fill in the table below. So here we have a clear trend. So I'm going to take a ruler and I'm going to place it on here in what appears to be the best fit to all of these points. And then I'm going to draw a line. Next, I'm going to look here. It says a distance of 20 megaparsecs. So we're going to look up here at 20 megaparsecs, and we're going to read off a point here on this axis here, which is the velocity. And we're going to do the same thing for 40, 60, and 80 megaparsecs. I find that the best way to do this is to basically use a ruler and line it up like this, and then look at this point right there, and then notice that this point there is going to be the corresponding point to the 20 megaparsecs. Then I take my ruler and hold it horizontally like this, and I can draw a line that appears to be parallel to this, that goes through the 20 megaparsec point and this line. Now let's do the same thing for 40, because that's right here. So 40 megaparsecs crosses right there, and we can take a look and make sure these look pretty parallel. And let's do the same thing at 60 megaparsecs, which is somewhere right about here. And the same thing at 80, which is the edge of the page right here. Now, what we can do is we can read off on this axis what each of these numbers are, which is the recessional velocity, and fill it in down here. So I have done that. I've drawn all my lines, and now if I follow this over here, I can see that that's about, it's probably about 1,400 kilometers per second. So I've written down here 1,400 kilometers per second. Now, looking up here at 40, it's right here, so that looks like about 2,800 kilometers per second, and this looks like about 4,200 kilometers per second, and that looks like about 5,800 kilometers per second. So my table looks something like this. Notice, as the distance gets further, the speed that the galaxies are moving are increasing on average. Now notice also there are some exceptions. There are some of these galaxies, let's say here or here, that aren't moving very fast compared to how far away they are. And there are some galaxies like this one up here that is moving very fast compared to how far away it is. So this is a trend, but it is not an absolute one-to-one correlation. The actual error bars are shown on all these points. So if you don't see an error bar, like here we have an error bar, or here we have an error bar, it means the error is smaller than the point plotted. So you can see it's a trend, but it's not a one-to-one relationship. So now turning to the second question, here's what it says. And the point of each of these is to kind of walk you through finding the age of the universe. So we now need to have what are called consistent units. It turns out that if you drive somewhere and let's say you're measuring your velocity in miles per hour and your distance in miles, and you want to figure out how long you've traveled, that's pretty straightforward. You just take how far you've gone divided by how fast you're traveling, and it works out. But let's imagine that you're measuring your velocity in, let's say, kilometers per hour, but you measured your distance in miles. It wouldn't really work out very well. So in our particular case, we're measuring a velocity in units that are convenient for people who measure velocities of galaxies, which is kilometers per second. And we're measuring our distance in units that are convenient for people who measure distances to galaxies, which are megaparsecs. Now, it takes a long time for maybe something to travel a megaparsec if it's going 1,000 kilometers per second. So we need to come up with consistent units. One set of consistent units that's very common to do would be convert megaparsecs to kilometers. And we get a very big number. And that big number would be, we can put in scientific notation, and then we can work this out and find a time that it takes to travel that far at a given speed, let's say, in seconds. Well, seconds are a pretty short time interval, so we're looking for the age of the universe. The universe is a lot of seconds old. I mean, we're talking, I don't know, we'll find out, but my guess is billions of years. So, at least, right? So, why don't we instead think about units that are more appropriate for what we're working with? So in our case here, because we expect ages on the order of billions of years, and we're already working in units of megaparsecs, why don't we find our velocity in units of megaparsecs per billion years? And the G stands for giga, because that is the prefix for billion in the metric system. That said, here's what the problem statement says. As it turns out, sound traveling at a speed of 1,000 kilometers per second takes 1 billion years to go 1 giga year to astronomers, or GA to geologists, to travel 1 megaparsec. Well within two significant figures. Using this information, fill in the same table again, but express your velocity in units of megaparsecs per billion years. What does this say? Something traveling 1,000 kilometers per second, so I'm going to write that down. 1,000 kilometers per second equals, well, let's see, 1 megaparsec per billion years. So we're actually pretty lucky. It came out about a reasonable number here. 1,000 kilometers per second is 1 megaparsec per billion years. Therefore, 2,000 kilometers per second would be 2 megaparsecs per billion years, and so on up. So now, comparing what we were just working on here to what we have from before, from part 1, if 1,000 kilometers per second is 1 megaparsec per billion years, then 1,400 kilometers per second would be 1.4 megaparsecs per billion years. So I'm going to fill in 1.4 here. Similarly, 2,800, I'm going to say 2.8. And 4.2 and 5.8, because 5,800 divided by 1,000 comes out to be that. Now, the next part of it, we have to ask ourselves, how long ago were the galaxies here? In other words, the galaxies all look like they're moving away from us. Every single one of them does. So, how long ago were they here? So, what I'm going to do is I'm going to fill in the distance and the velocity, and then just like you would for your car, we're going to figure out how long ago we left. So imagine you left your house at a certain time and you drove for some amount of time at a speed of 1.4 megaparsecs per billion years, and you traveled 20 megaparsecs. How long did that take you? Well, it's just like if you were traveling at a distance at a velocity of where you're walking at 1.4 miles per hour and you went a distance of 20 miles, how long would that take you? It's a very similar problem, almost exactly the same. So, as we can see, if I took this number in megaparsecs and I divided it by this number in megaparsecs per billion years, I'm going to get something out in billions of years. So, let's do that. 20 megaparsecs divided by 1.4 megaparsecs per billion years is equal to 14. Okay, now let's try this again with this. If we've traveled a distance of 40 megaparsecs at a velocity of 2.8 megaparsecs per billion years, how long did that take us? So let's try that. 40 divided by 2.8 equals 14 again. So I will put my 14 here. And now, what if we're traveling at a velocity of 4.2 megaparsecs per billion years for a distance of 60 megaparsecs? How long would that take? So I take 60 divided by 4.2 equals 14. And the last one, 80 megaparsecs divided by 5.8 megaparsecs per billion years is 14. So, to two significant figures, they're all the same. Notice the numbers were not exactly 14, they just rounded to it. And that probably has to do with how well we were reading the graph on the prior page. So, to put it a different way, 14 billion years ago, all those galaxies were here. Or, we were the same place as all those galaxies, which may or may not be the same, because the velocities we're measuring is the speed between us and the galaxies. We're not necessarily fixed compared to some other place. We're just apparently fixed compared to where we were. Presumably, if we lived in one of those other galaxies, and in one of those other galaxies we measured the distances to our galaxy and the speed that our galaxy was moving, and to a bunch of other ones, we would get the same thing. Clearly for our galaxy we get the same thing because we'd have the same distance and the same velocity. The velocity is just going the other way and the distance is going the other way, but the amount of time is the same. So, the next part, it says, notice that this time, which is the 14 billion years, it's the same time for all of the galaxies, because the further away the galaxies are, the faster they move. Remember, velocity was proportional to the distance. Find the average travel time which is called the Hubble time, discuss why astronomers therefore believe this to be about the age of the universe. Well, clearly the average of 14, 14, 14, and 14 is 14. Now, if we had saved another digit for each one, then maybe we get something a little with another digit. But quite frankly, the data we were given was only pretty much good enough to 2 digits. So for this part here, you will discuss in much the same way we were just talking about why astronomers imagine this to be about the age of the universe. Think about it this way. According to these data, 14 billion years ago, each one of those galaxies was here, which means that we were at the location of each one of those galaxies, which means that we must have been all in the same place. So imagine it like you're off at college and everybody leaves the same time to go off for break. But some people drive away faster than others. The people drive away faster will have gone farther after, let's say, a couple hours driving. And the people who drive slower won't be as far away after a few hours driving, the same amount of time. But if you took the distance everybody traveled divided by how fast they went, you would get the same amount of time ago that they left. So finally, you can answer another qualitative question. So, the fastest anything can travel is the speed of light, which is about 300,000 kilometers per second. If the universe started at one point and has been expanding ever since, what must be its radius? Express your answer in megaparsecs. So, what this is imagining is that everything started at one point and then moved away from there. So, the fastest anything could ever move is the speed of light. So, based on the analogy of everybody leaving school at the same time, let's imagine that the fastest that a car can travel on average is 70 miles an hour. Well, then whoever that is the person furthest away. Now, clearly, the size of the Earth and so on is much bigger than that. But the premise here was if the universe started at one point, that means that everything was at one point. So if all those galaxies were at one point and everything else, it's been expanding ever since. So what must be its radius? So, if this is where the universe started, as we imagine it, and everything moved away at, let's say, the speed of light, which is the fastest anything can travel, then there's a certain size, a certain radius the universe can be. Well, we've just calculated how long the universe has been expanding for, and we know that the speed of light is 300,000 kilometers per second. We also know that 1,000 kilometers per second is 1 megaparsec per billion years. Therefore, 300 megaparsecs per billion years is the same thing as 300,000 kilometers per second. We also know from common sense that distance is velocity times time. If you traveled at 60 miles an hour, for 2 hours, you've gone 120 miles. So, we take a velocity of 300 megaparsecs per billion years times 14 billion years. The billion years cancel. Then we take 300 times 14, which comes out to 4,200 megaparsecs, which is actually quite close to what we estimated based on the graph that was plotted on the prior page. Therefore, based on these data, the size of the universe is about 4,200 megaparsecs, or, a little more than 4,000 times the distance from here to the Andromeda Galaxy. Now, one final point of note. What this time is called the Hubble time, because the relationship here was called the Hubble's law. And remember, it probably shouldn't be called Hubble's law. It's probably called Lemaitre's law or Slipher's law. But nevertheless, that's what it's called. And the slope of this graph, if we find some point, let's say here, and say, oh, let's find the slope of this line. What's the rise over the run? Well, the rise from about 0 to about 5,000 kilometers per second is 5,000 kilometers per second. And the run is about 70 megaparsecs. So if I then take 5,000 kilometers per second divided by 70 megaparsecs, I get something like 71. And when you find a slope of a line on a curve, on a graph like this, the units are always whatever the units are on the vertical axis divided by whatever the units were on the horizontal axis. So the Hubble constant, based on this graph, would be 71 kilometers per second per megaparsec. It's kind of hard to think in these units physically, but it makes a lot of sense from the point of view of people making the observations. Notice something. Kilometers and megaparsecs both measure length. So this measures inverse time. Also notice something else. We calculated this by taking the speed divided by the distance, but we calculated our Hubble time by taking the distance divided by the speed. Therefore, Hubble's constant is equal to 1 over the Hubble time. So you can also say that this is equal to 1 over 14 billion years. Now, if you have different unit systems, you can treat that as proportionality if you want to. So we can think about it as, well, what if the Hubble constant was twice as big? Then we'd expect the Hubble time to be half as big. And what if the Hubble constant was half as big? Then we would expect the Hubble time to be twice as big. So in about 14 more billion years, we'd expect the Hubble time to be about 35 kilometers per second per megaparsec. So that is how we calculate the age of the universe from distance and velocity data to various galaxies. Thank you very much for listening.